So I think it is worth saying or reiterating that I'm an igneous and structural geologist, and most of my interest to date has focused on the geometry of intrusions and emplacements. The economic side of them has always interested me, but I've never really got involved in any of that sort of work. So it's really great to be here today talking to you guys who know a lot more about that side of things than I do. So I am going to try and talk about how my work may fit in to things like improving the efficiency of exploration. But do bear with me if my talk bit of the economic geology is a bit limited. It's been really good joining this symposium so far, and I've certainly learned a lot. And I think it's fair to say that a lot of the work that we've really progressed in over the last decade or two has been along the petrological and the geochemical side of understanding magma-related ore deposits. Yet I find, and this is the same with most aspects of volcanology, that the structural understanding of magma emplacement or the shape of the intrusions, our understanding of that is often a bit more limited. And I think that can simply be put down to the resolution of geophysical data, and we can generally only access the Earth's surface. Okay, once we've found an ore deposit, we may be able to then put lots of boreholes down and constrain its 3D geometry really nicely. But in the early exploration phase, we don't have a huge amount of data to work with in terms of understanding magma emplacement or intrusions in 3D. And that's what I sort of want to talk to you about today, is seismic reflection, perhaps how we can use it in exploration, but also mainly how we can use it to look at potential analogues for the intrusions that we're interested in economically. And where's my mouse gone? So this first image here, I think this is just really quite fantastic. This is from offshore southern Australia. This is the seabed up here. Here we've got some ancient 42-million-year-old volcanoes. We can map out the external morphology of volcanoes, just like you go flying past in the Andes or something. We can look inside the volcanoes, map out their internal architecture. And what we're interested in today, we can look at that underlying plumbing system, not just the shape of these intrusions in 3D, but also the associated structures and how they were accommodated. So mostly what I'm going to be talking about today are sills and sill complexes. That will become apparent when I give a bit of a brief intro to the seismic reflection technique. And I'm sure we're all well aware of what a sill looks like. And perhaps even some of us are aware of just how extensive these interconnected networks of sills can be. Here's the Karoo Basin in South Africa. All these black marks are outcrops of sills at the surface with an interpretation of how they may be linked at depth. And this is an area the size of Spain, and that's just mind-boggling to me. And so understanding these systems can be really quite important. Moving on. Sorry, computer's a little bit slow. So before I get into talking about what we can actually do with seismic reflection data, I thought it best to give a bit of an introduction to the technique. It's perhaps not something you would have come across in more in the mining industry, although I'm sure some of you are familiar with it. So we all know what an earthquake is. It's basically a source of acoustic energy that moves through the earth. For seismic reflection data, we use our own man-made active source, and this should be a video that's playing, but it's not. Anyway, it simply shows that there's acoustic energy that travels down from this active source. It reflects off boundaries between rocks and comes back up where it is measured at the surface. Let me just see if I can get this playing. It should do it automatically, but nope, sorry about that. So that's what the image is supposed to look like in the end. And by collecting and stacking all this information together, we can start to build up a 3D picture of what the Earth looks like in the subsurface. So here we've got a nice example of what our cartoon schematic would look like and what the actual data looks like. And there's a few little points to bring together here. So the first is that the acoustic energy reflects off boundaries within the Earth that have different physical properties. So that could be boundaries between a sedimentary rock and an igneous rock, or it could be boundaries between water-filled sediment and oil-filled sediment. And the larger the contrast in the physical properties, the more energy that gets reflected. Just try and put on the laser pointer, which I seem to have lost the ability to look at. Technological issues, eh? So in this seismic data, you can see here that we have some quite prominent reflections from those strong physical contrast boundaries, but then within some units, they look very fake, very translucent. And this is probably an area where we've got, for example, mudstones on top of mudstones on top of mudstones. Whereas in other areas, we may be having interbedded mudstones and sandstones, and we can start to build up this 3D picture. Okay, slide's not progressing at all now. Okay, so I'm really lucky because I'm quite simple when it comes to maths and geophysical methods, but seismic reflection data, because we're relying on the physical contrast between different rocks to image a structure, there's a big contrast between sedimentary strata and igneous rocks. So they really stick out like a sore thumb. They're really obvious. They form these, what we call these high amplitude, these bright reflections. Excuse me. So not only can we see them in cross section as we see here, and there's multiple types of intrusion geometry, but we can also map them out in 3D as well. So here's our strata concordant sill, and here's this what we call a saucer shaped sill. This is quite a common geometry that we see within this sort of data. We can look a bit closer and we often see there's little disruptions within these reflections that we can relate to magmatic steps, and there are things that I'll come on to later. But ultimately, at the end of the day, these are just geophysical images. Most of the time, they're not, the intrusions aren't penetrated by boreholes or anything. So how do we actually know they're igneous? Generally, we don't. We sort of have to assume. But one of our biggest steps is to look for analogues. And just like in many other disciplines, trying to find what we're seeing in the subsurface at the surface is really quite critical. So here's just some examples of how the geometries that we can interpret in seismic reflection data compared to those that we may see at the surface. There's a few little things to note here. So one is that most of the data that I'll show you will be presented in time. So that's the time it takes the acoustic energy to travel down from the surface and back up. If you know things about the seismic velocities of the rocks, you can depth convert that, but we're often lacking that information. So that does mean that the vertical scale here is a bit distorted to what the intrusions would actually look like. So just bear that one in mind. The other one is that most of the data I'm going to be showing you comes from sedimentary basins. Now, that's not too much of a problem. Oh, I was expecting a different slide there next. I'll come back to that one in a minute. So that previous slide shows some examples of sills in seismic reflection data, but we can also look at these sill complexes. So here's some imagery from, excuse me, from offshore Ireland. And we can see we've got these high amplitude reflections, these sills, transgressing up through the sedimentary strata. We can see in places that they appear to be feeding each other. And if I just put on the interpretation to clear things up a little bit. So this example is being imaged over about 15, 20 kilometers, and we can look at them in 3D. So this is a bit of a complex figure, but each of these colored sills here, with purple being deep, the reds being shallow, you can see that they all sort of meld together. They're all connected across quite a broad area. So we can image these sill complexes and map them out in 3D, which we just can't do at the surface. Just waiting for the next slide to come up. Okay, so I mentioned that most of the examples I'm going to be looking at are in sedimentary basins, and we may expect sedimentary rocks to behave differently to crystalline rocks, but we see very similar structures of sills and sill complexes within crystalline rocks. So a couple of examples here. Here's one from the Yilgarn Craton in Australia. Beautiful seismic line, really incredibly long, and there are these rather bright high amplitude reflections that I've overlaid in black here, and where these crop out at the surface, they correspond to sills. So we can see these really laterally extensive interconnected sills within the crystalline crust. And an example from the North Sea, here we've got our sedimentary basin, this is our crystalline basement, and there's a rather prominent high amplitude reflection down here, which when you map it out, has this sort of geometry. It contains portions that are a bit saucer shaped, I always struggle with that phrase, saucer shaped, and often quite a few what are apparently low bait type structures, again, which I'll come back to. And seismic data has been used to look at magmatic ore deposits as well. There's a lovely example the other month of some work that's been done on the Nova Bollinger deposit, and some beautiful 3D seismic reflection imagery of that. I just wanted to show a couple of examples from the Bushfield. This used to be one of my favourite ever seismic lines. It looks as though it's just a sedimentary basin if you don't know what any of the words mean, but actually what you're looking at here is reflectivity from some of the reefs and some of the different layers within the Bushfield, and you can just start mapping them out as to what that attitude is in the subsurface. I thought this was great, and then I came across a paper last week as I was putting this talk together, and just to build the suspense, PowerPoint's being slow here, it looks like this. So this is 3D seismic reflection data over the parts of the Bushfield. You can see these beautiful igneous layering. You can see the potholes where a lot of the resources are accumulated, and you can map out these potholes in 3D. You can measure their dimensions. I just think this data is really quite fantastic. So this gives us something that we just can't get from looking at rocks in the field or from sinking loads of boreholes and trying to interpret between them. So part of the talk was about unraveling sill emplacement history, and hopefully I've showed you so far that we can look at the geometry of sills, but in order to unravel its emplacement, we need to try and pick out some sort of temporal type construction to the sills. And this comes to those lobes and those sort of linear sort of features that I was mentioning. So this is a map, a seismic map of a sill in the Faroe Shetland Basin. What my colleague Nick has done here is he's made basically the only thing visible to be these high amplitude reflections. So these are some seismic lines through this sill. You can see that there's lots of reflectivity in this section, but the sill itself is very bright. So if you make everything else transparent, you're left with just looking at a rendered image of the actual sill. And within this sill, you can note that there's little vertical offsets, some little overlaps within these segments, and it gives this sort of lobate type structure. Now, how would we interpret that? Well, this goes back to thinking about what we might see in the field. And just like we do in the seismic data, in the field, we often go and look at sheet intrusions, and we can see that there are these little offsets, these little vertical steps, or these little bridge structures. And these form because sheet intrusions generally propagate as little segments. So they're not originally continuous sheet intrusions, they propagate as segments that as magma flows into them and they start to inflate, they start to coalesce into what we see as the continuous sheet intrusions. One of the critical things about these structures is that their long axis is parallel to the magma flow axis. So by recognizing these in seismic reflection data, we can start to map out magma flow pathways within the sills. And that allows us to identify things like source position and emplacement history. So I'm hoping that this video is going to work. And what we're looking at here is we're still dealing with this sill intrusion. What we're looking at is an oblique view through the seismic 3D volume. All the dim reflectivity has been made transparent, and we're just looking at the sill. And because from these lows and these steps we've been able to interpret the flow direction, what we're going to do is step through the seismic data on a plane orthogonal to that emplacement direction, and we're going to watch the sill intrude effectively. So, is it going to go? No, it's not. Oh, that's really disappointing. Okay, unfortunately, that's not working. It was working about 15 minutes before I joined the Zoom call, so there must be some issues there. But what we can do is we can use these structures throughout to try and put together the emplacement of entire sill complexes. So this is a zoomed out view of some sills. If we just zoom in a bit, your eye is sort of drawn to this ragged edge to the sills, and within it, there looks to be these sort of like quite sinuous channel-y type features. Put on a little bit of interpretation, and you can check this by looking at the cross section, see whether they do correspond to these steps or not. And we can understand how entire sill intrusions develop. So this is an example from the Ferro-Shetland Basin, of which this sill complex is just a small portion. And by doing this, we were able to map sills all around, and map out flow indicators all around, and pick out that the magma was basically coming up basement-involved faults. It was traveling through the basement via these faults, and once it got into the sedimentary basin, it was spreading out laterally to form this really quite complex sill complex. So what I wanted to try and do, and this is sort of a prelude to Jonas's talk next and then Uchi's afterwards, is to highlight why understanding these flow pathways within 3D seismic reflection data can help us in exploration. So I'm sure many of you are aware that a lot of the magma-related ore bodies that are economically interesting are associated with rather oddly shaped intrusions, namely these sort of chonolith, these tube-like sort of features, these sills that have become tube-like in appearance. And really our understanding of how these structures are in place, and therefore how associated ore deposits are structurally controlled, is quite limited. But there is quite an interesting similarity between what these features look like at a slightly larger scale compared to what some of these internal flow related features look like in sills and sill complexes. So these are what we call magma fingers, or what I would call magma fingers. Quite similar to the formation of steps and bridges, except that they generally involve some sort of ductile behavior or fluidization of the host rock. And in 3D, our suggestion is that they may look quite similar to these chonolith bodies, and you could imagine that if magma was preferentially funneled into one of these, its inflation could end up producing something like this. Now, as I mentioned, Jonas is going to be looking at this next, but we've got some examples where we think we can see these sort of fingers in 3D. So perhaps we can start to quantify that shape and sizes and comparisons to chonoliths a bit more and really get at that emplacement. I'll leave that to Jonas to talk about. Okay, so one of the other things that I wanted to discuss was how do we make space for magma emplacement? So the great thing about seismic data is not only can we look at the geometry of the intrusions and try to reconstruct how they are intruded, but we can look at how space was made around them. And that's important when we think about fracture networks and fluid flow, for example. So one of the things you'll notice with the seismic reflection images that I showed is that generally we deal with quite shallow intrusions that are in place and there's uplift above them. So the main mechanism of uplift is what we call force folding, the uplift of the overburden. So here's a nice example of a sill that I showed earlier. And this is a map showing this domal fold structure at this horizon level in here. We know that this was the paleo surface at the time of intrusion because we can see sedimentary strata onlapping onto it. And there's also a little volcanic mound as well, the origins of which I'll sort of come back to a little bit later. So we can start to understand how the intrusion was accommodated. Here's a nice example from offshore New Zealand, where actually we can see that there's some interesting seismic stratigraphic relationships and distributions of sedimentary strata across the fold. Without going into detail, it basically looks as though we've captured the sill inflating and the rock above uplifting, the sill deflating, and then the rock above subsiding, and then uplifting, subsiding. And basically, it looks as though we've got a series of sill emplacement events over about 30-odd million years, if you trust the well dating. So we can start to get at the temporal aspect of emplacement as well with these sorts of structures. And that can allow us to try and understand how the magma was intruded, but also think about, as I've mentioned before, the controls of potentially mineral-bearing fluid flow in fracture networks, or the capture of these sort of fluids within folds and things. We can do the same when it comes to sill complexes as well. So this is the same sill complex from the Irish Rockall Basin that I showed you earlier. Each of these bright reflections is an intrusion, and you can see the fold above. There's multiple folds, quite interestingly. So what we think is going on with this being the 3D view is that we have a system where we've got sill intrusion, we've then got more sill intrusion, but because they're occurring, excuse me, at pretty much the same stratigraphic level, the folds above are merging and becoming compound folds. So we can have this broad uplift across entire sill complexes, explaining how we accommodate such volumetrically large areas of magma. With the importance here being that fluid flow can get directed up these folds, we can affect sediment routing. So although there may be no direct effect to magma-related ore deposits, potentially sedimentary-related ore deposits and sediment routing can be affected. And there has been some work done on this and on some areas offshore Madagascar, I think. Okay, so to move on to a more direct lesson for exploration, as it were, let me take you through this slide. So this is a map at the bottom of a sill imaged in seismic reflection data offshore Australia. The white lines are where it intersects pre-existing faults. The dashed white lines are maps of these intrusive steps, and what we're seeing up here is a oblique view of a seismic section, and this fault F3 as a semi-opaque fault plane. And what I've coloured on is amplitude across the fault. So where this bright high amplitude sill crosses the fault, there's a yellow brightness to the fault. And as we step through the seismic data, we'll see that, for example, here, the sill is cutting straight across the fault. There's no offset at all. But then as we move further along, we start to see a step developing as magma eventually starts to intrude up the fault. These sort of pale white areas are showing where magma is intruding up the fault. You can see that it's not uniformly distributed. And the idea here is that where magma is flowing towards the fault in its hanging wall, the uplift accommodating intrusion opens up the fault and magma can go up. and vice versa when it's in the footwall, with the uplift actually closing the fault. And this is really quite similar to what we see in some of these sills and skarn complexes in Canada, where you can see the sills going up some faults, and where we have that transition from horizontal placement up the fault, we get the focusing of magmatism. We've got enhanced fluid flow, and there's skarn deposits. So from my perspective, I'm interested in the combination of faulting and folding that controls intrusion geometry, but I think there's quite some interesting applications there to ore deposits as well. I just wanted to finish with a few other quick ideas where I think seismic reflection data may be able to help us. So I've showed this image before of layered intrusions, and I think it's quite interesting that you know, there's sort of that growing idea that the accretion of different sills or the intrusion of sills within crystal mushes can create some of these economically important layered deposits. And it's some interesting work done on the rum intrusion recently, and it sort of starts to make you think whether we could see these sorts of things in seismic reflection data, particularly if there's a physical difference between these, you know, sort of later sills, as it were, and the mush that it goes into once everything's crystallized. I think there would be, and there's some hint of that. So this is a bit of a complicated image from some work recently published by Faye Walker up in Aberdeen, but it shows really nicely by comparing seismic data with gravity data that in order to accommodate what we're seeing in the seismic imagery here, there really needs to be a layered intrusion. Now, whether that's layered with magma sheets and then interlaid with sedimentary bodies, or different types of magmatic layering, it's sort of a bit questionable, but it does show that we can probably, or perhaps start get at trying to understand how layered intrusions may be generated with seismic reflection data, or how it can at least help. So I mentioned earlier that there's this little vent above this intrusion. It could be a little volcano, but it could also be some sort of hydrothermal vent. Hydrothermal vents are something we really quite commonly see in seismic reflection data. So here's some examples that I've worked on from offshore northwest Australia. These ones, they're not directly associated with underlying intrusions, but there probably is a magma-related fluid origin. And you can see that they occur across quite a vast area. And we see similar things to this all around the world in various sedimentary basins. And what was quite interesting as I was putting this together, and as I've spoken to a couple of people over the last few years, is the idea that actually there's quite a striking similarity between these and things like VMS deposits. But as far as I'm aware, nobody's tried to make the link that some of these, what we call hydrothermal vent complexes, could actually be VMS deposits. If anything, I think they probably provide an interesting analog into that formation. So I think there's something to look at along these lines as well. The last thing I wanted to mention was dikes. I always get asked, well, you're looking at seismic reflection data. Reflections tend to bounce off things that are subhorizontal to get back to the surface. If things are vertical like dikes, it just goes deeper down, so you don't see anything. So how do you know sills and sill complexes are so important? You know, what's the role of dikes? Well, we can see dike intrusions in seismic data in places where the dike swarms are tilted. For example, here's one from offshore Norway, and you can see these inclined reflections. They cut across the background stratigraphic reflections, so they're not just faults. They've been tilted due to fault activity. But what's interesting here is note how the footprint of the dike at different structural levels, its width decreases upwards. And here's some vertical examples that I've recently worked on in seismic reflection data, where we can see vertical dikes as little disruptions in the seismic reflection data, and we can map these dike swarms over really quite a large distance, and we can start to understand their 3D structure as well. We can look at the faults that are generated above these dikes, and they tell us something about how the dikes were intruded. So even with seismic reflection data, we can start to get at dikes and dike swarms, and potentially that will lead on to associated ore deposits as well. So that sort of leaves me just to conclude that I think the structural understanding of plumbing systems often lags behind a little bit for very valid reasons, but I think that seismic reflection data provides a really unique opportunity to try and get into this. And is actually quite a really good way of bringing lots of different people together. I think there's lots of different indirect and direct implications for economic geologists, as it were, whether it's just looking at the fundamental understanding of magmatic processes or actually using the technique in exploration and that. So hopefully this talk has been of interest to you, and I would love to hear from you about the potential uses that you could envision of seismic reflection data. So thank you very much.